Yes, I will start.
Yeah.
Okay. It's time to start, I think. Okay. Let me introduce today's speaker, Professor Tatsuya Miura. Professor Tatsuya Miura got PhD 2017, and after that he received several prizes for young researcher. And he moved to, he received PhD in University of Tokyo, at the University of Tokyo, but he moved to Tokyo Institute of Technology, and recently this year he became an associate professor of Tokyo Institute of Technology. His main interest is higher order elliptic and parabolic PDE related to geometry. And today he is going to talk on Li-Yau type inequality for curves and application. Please.
Thank you very much for the introduction. So it's my great pleasure to be part of this great seminar, great Asia Pacific seminar. So in this talk, I would like to introduce you my recent results on Li-Yau type inequality for curves and also its several applications. Okay, so first, I give you some brief introduction about the bending energy and self-intersection because both of them are directly related with the main result, which is Li-Yau type multiplicity inequality for curves. And after that, I give you some applications to elastic flow, elastic network, and also elastic node. Okay. And this reference is, I mean, most of the contents of this talk is contained in this reference. Okay. So first, I explain what is a bending energy. So the bending energy is a quantity that measures how a given curve or surface bends. So for curves, I mean, in this talk, we mainly discuss curves. So this is the definition of the bending energy for curves. And here, this gamma is a curve in Euclidean space, and S denotes the arc length. So this is the line integral, and the integrand kappa denotes the curvature vector, which is the second order arc length derivative of the curve. So this is a kind of, I mean, curvature square. This is also called total square curvature, but it actually measures how a curve bends. In fact, if a curve is straight, then this bending energy is trivially zero. And if the curve highly oscillates, then the bending energy becomes larger and larger. Okay. And this bending energy has a long history. And actually, this is defined by Daniel Bernoulli already in 1742. And shortly later, Leonhard Euler studied this variational problem of this bending energy. And also Max Born, who is a very famous physicist, who is famous as his fundamental study on quantum mechanics, but actually his dissertation is about bending energy. So anyway, this has a long history and very classical problem. And why this is important? This is because if we minimize the bending energy in a certain class of curves, then it is known that the minimizer often realizes the shape of some real object. So this energy can be, this variational problem of the bending energy can be used for modeling real phenomena. So the critical points of bending energies are important. And so a critical point and the fixed length constraint of the bending energy is usually called, nowadays called Euler's elastica, or simply elastica. Okay. And this is some examples of elastica. And actually these figures, these beautiful figures are already drawn by Euler himself. And Euler classified the possible shapes of elastic A into several classes. And so these are not all, but actually there are candidates in, continuously many, uncountably many candidates that Euler have chosen some representatives of them. Okay, but anyway, you find here some kind of figure-eight shape, and now that this is called figure-eight elastica. And this shape is extremely important throughout this talk, so please remember this figure-eight elastica. Okay, and later, Max Born did some real experiments and compared the experiments and the theory. And actually, he found that, for example, this is a some planar elastic rod, and this shape resembles a part of Euler's figure. So actually, this model can be used for analyzing the real shapes. Okay, and this is a very classical theory, but recently, it is known that the effect of self-intersection is more complicated shapes. And this is one example. This is an experiment on so-called elastic knots. So it's a knot shape made by some closed stringy wire. But this is a hose, but anyway. And now you can see some more complicated shapes. For example, these are multifold circles. And also this is a non-planar, some spatial shape. And this is a composite of a circle and a figure eight. So, and this is a figure eight again. So you can see some complicated shapes. And actually, theoretically, this is due to the effect of self-intersection. So for this reason, it is quite important to understand the relation between the bending energy and self-intersection. Okay. And here, now we address some more fundamental problem, which we call Li-Yau inequality. And Li-Yau inequality studies the quantitative relation between the bending energy and self-intersection. Okay. Okay, so now that's all about the introduction, and I now enter about the main result. So in order to explain our main result, which is Li-Yau inequality for curves, it is good to quickly review the classical Li-Yau inequality for surfaces, two-dimensional surfaces. Okay, for two-dimensional surfaces, the bending energy is defined by the square norm of the mean curvature vector. So it's, in a sense, reminiscent of the previous one-dimensional case. And this energy is also called Willmore energy. And I think the name of Willmore energy is much more famous, nowadays much more famous in mathematics, in particular in geometry. But because of its physical origin, this energy is also called bending energy. So here we adopt this name. Okay, and this Willmore bending energy has several important properties, but let me mention some of them. So first, the bending energy is scalar invariant quantity. So the bending energy is actually invariant with respect to any similar transformation. So in particular, it's invariant with respect to dilation, any dilation. Okay. And also, another important point is that the bending energy is minimized by a round sphere among all closed surfaces, two-dimensional surfaces. And actually, this is known as the classical Willmore inequality. So, but anyway, so in a sense, this bending energy measures roundness of a given closed surface. Okay. And next, we define multiplicity. So if we say that a two-dimensional surface sigma has a point P of multiplicity K, if the given surface passes the given point P at least K times. So in particular, if the given surface sigma has a self-intersection, then it means that there is a point of multiplicity 2, at least 2. And conversely, if the surface is embedded, then for any point of the surface, the multiplicity is equal to 1. Okay. And for these notions, the classical result of Li-Yau asserts that if a closed surface, two-dimensional surface in Euclidean space of any codimension has a point of multiplicity K, then the bending energy is bounded below by 4 pi times K. So, I mean, if the multiplicity is higher and higher, then the bending energy is higher and higher. But, intuitively speaking, this means that in order to pass a given point many times, then actually we need more, bending behavior for in the surface. So this is actually quite intuitive result, I think. Okay, and this inequality is quite important, and I give you several remarkable points of this result. First of all, this inequality is sharp in general, in the sense that for nearly K times covered spheres, the bending energy takes almost 4 pi K. So this lower bound 4 pi K cannot be improved. And what is the nearly K times covered spheres? It's actually, so for example, if K is equal to 2, then it's simply something like this. For a given this kind of curve, if we revolve this curve, then we can make something like nearly 2 times covered sphere. And here you have multiplicity 2. So this surface has multiplicity 2. And actually, it looks like 2 times covered spheres. And actually, the energy is almost 8 pi. So in a similar way, we can construct a general example of general multiplicity. Okay. So this is one important point. And the next important point is if the bending energy is less than 8 pi, then the closed surface sigma must be embedded. And this is a quite direct consequence of the contrapositive of the Li-Yau inequality. But this is actually quite important because in this similar quantitative criterion, we can always ensure the embeddedness of a surface, closed surface. So this criterion is quite compatible with the studies of some gradient flows or some minimizing problem, variational problem of the bending energy. And actually, this criterion has been used in as a fundamental tool in many important studies. And so I give you some example. One is the Kuber-Shaitsley's study of the Wilmore flow, and the other is Marcus Neves' study on the Wilmore conjecture. Okay, but anyway, so an important point is that Li-Yau inequality is so important. Okay, so now this is the end of the quick review of the classical Li-Yau inequality. But actually, the proof heavily relies on the two-dimensionality. And actually, this Li-Yau inequality has quite special properties of two dimension. And actually, there is no direct extension to other dimension, even for lower dimension 1D. So our natural attempt is to study one-dimensional counterpart of the Li-Yau inequality. And now we found some kind of optimal Li-Yau inequality, but actually we also found some new phenomena due to low dimensionality. Okay. So now our goal is to establish a Li-Yau type inequality for closed curves gamma in Euclidean space. Okay, but one point here arises. It is that the bending energy B, this is for curves, bending energy for curves is not scale invariant. Actually, if you consider simply a circle, it depends on the radius. And if the radius tends to infinity, then the bending energy goes to 0. So actually, this bending energy is not scale invariant. So it doesn't measure the roundness of a closed curve, for example. So this doesn't directly correspond to the previous two-dimensional bending energy. So for this reason, we consider a slightly different quantity, which is the normalized bending energy. And this normalized bending energy, B bar, is defined by the original bending energy multiplied by the length. So in other words, the bending energy normalized by the length. And thanks to this normalization, we can easily see that this normalized bending energy is scale invariant. So it's invariant with respect to any similar transformation again. Okay, so from now on, we mainly consider this quantity. And actually, I would like to mention that this normalization is equivalent to assuming that the length is equal to 1, because we are now working on the class of closed curves. So this class is closed, in a sense, closed with respect to dilation. So it is actually equivalent to fixing the length. But anyway, we consider this normalized bending energy. Okay. And it turns out that this is a kind of right quantity to consider, because now for any closed curve gamma in Euclidean space, the normalized bending energy has a non-trivial lower bound 4 pi squared. And in fact, the equality holds if and only if gamma is a round circle. So the equality is in particular attained, and also it is attained only by a round shape. So now we found another common point with the original two-dimensional bending energy. So this normalized bending energy is now, we found that this is quite right quantity to consider, natural candidate to consider. Okay, then our precise goal is now to find an inequality for gamma, curve gamma, with a point of multiplicity k of the form of this form, So the normalized bending energy is bounded below by some constant times k squared. And now we found a new exponent squared, but this is natural in view of easy scaling argument. So this square appears naturally by scaling. So the important point is to find an appropriate C. So this is the main difficulty to establish this inequality. Okay. Okay, so now I would like to explain my main result on the one-dimensional Li-Yau type inequality. And here we give pi star, which is some kind of universal constant, but I don't enter the details, but this is kind of universal explicit constant. Actually, this can be defined by elliptic integrals. So by using this constant, we have the following statement. So let first gamma be a closed H2 curve in Euclidean space of any codimension n. Any dimension n. And here we specified this H2 Sobolev regularity But this is quite natural in view of the bending energy because it's given by the square norm of the second order derivative, involving the second order derivative of the curve. So this is a natural Sobolev regularity. And now we assume that this curve has a point of multiplicity k, and k is larger than or equal to 2. And then we have the desired form of the Li-Yau inequality. So the normalized bending energy can be bounded by pi star times k squared. Okay. So now we found the general inequality, Li-Yau type inequality. But as I said, the classical Li-Yau inequality possesses a very nice optimality result. So the classical Li-Yau inequality is sharp in any codimension and any multiplicity. So we are naturally interested in the optimality of this inequality. And then we found some interesting new phenomenon compared to the two-dimensional case, because the equality of this inequality holds if and only if the dimension of the dimension n is greater than or equal to 3, or the multiplicity k is even. So we need some constraint on the multiplicity or dimension or codimension. And so if equality holds, then it needs to be a k-Lift elastic. So we have a strong rigidity on the shape of the equator, the minimizer. But anyway, this k-Lift elastica is a new notion, and this is not yet defined. So I will give you some brief definition later. But anyway, now I just mentioned that we have a strong rigidity result. Okay, and now we have in many cases equality holds in this inequality. But how about the remaining case? So we have optimality in many cases, but we have missing case. And concerning this missing case, we actually found exhaustive non-optimality result. So more precisely, on the other hand, if n is equal to 2 and k is odd, which means that if a curve gamma is planar, closed planar curve with odd multiplicity, more than or equal to 3, then there exists some positive constant that depends on k, such that the above inequality can be improved by an addition of epsilon k. So we have something like new phenomenon, which is in this missing case, we have non-optimality, more improvement of the inequality. Okay. And so let me give you some several remarks. First of all, this result is new in many cases, but in the special case that nk is equal to 2, which means that for closed planar curves with multiplicity 2, recently Miura and Rupp obtained this same optimal estimate with the rigidity. Yes. But our results is new for all n greater than or equal to 3 or k greater than or equal to 3. Okay, and also I should mention that the non-optimal estimate of the form of this form, b bar, is bounded below by some constant, some non-optimal constant c times k squared, has been known. Obtained by several authors, for example, by Polden or von der Moser or Wheeler. I think they obtained independently. And also there are some other references that obtain this non-optimal estimate, but this optimal estimate is new, I should say. Okay. And the proof of this result is mainly variational. I don't enter the detail of the proof, but it is variational. And we heavily use the non-classification of elastic A due to Langer and Singer. And also we give, for non-optimality result, we need to use more, and the proof is actually based on some transcendency result for some values of Gaussian hypergeometric functions due to Yves and Andre. Okay. Okay, so this is the main result. But now I haven't yet explained what is a K-lift elastica. So we need to I need to explain this K-lift elastica. K. So K-lift elastica is defined by the composition of some K half-fold figure eights of same length. And figure eights means the given, previously mentioned figure eight elastica, which has been essentially obtained by Euler. And so the figure eight elastica looks like this. And here half-fold figure eights means that, this part. For this part, I call half-fold figure eights elastica. Okay, and this is, and the composed means that this half-fold elastica K are connected at the vertex here. Here, this red point, so this red point is a vertex. Okay, so this is a rough definition of K-lift elastica. So by definition, so let me see some examples. By definition, a two-lift elastica is up to invariances given by a unique figure eight elastica, classical figure eight elastica. So because we need to connect them in order to be the curve being at least C1 because it belongs to H2 curve. So by Sobolev embedding, it has C1 regularity at least. So in order to connect in this way, we automatically have that any two-lift elastica is a unique figure eight elastica. So it is in particular analytic curve, and it is planar. Okay. So this reveals that our result also covers the previous Marius and Miura's Miura and Rapp's result. Sorry. Okay. So this is okay. Now this is a classical shape, but for higher multiplicity case, we found some new optimal shapes. And the most important case is the multiplicity 3 case. In fact, for any three-lift elastica, it's again up to isometry, up to invariances given by a unique shape, which we call elastic propeller. So this is a new shape which I found. Okay, and this actually looks like propeller shape. And now you find that this shape is not planar but spatial. So this is actually spatial shape. So it is important to have higher codimension in this case. And this elastic propeller directly explains why higher codimension is needed to obtain optimality in the case of multiplicity 3 or higher order multiplicity. Okay, and this is one of our main findings here. And for more higher multiplicity, then actually K-lift elastica are generically not unique, but actually we have strong rigidity due to its definition. So the shape is quite restricted. The possible shapes are quite restricted, but actually we have no uniqueness, such as two-lift or three-lift case. Okay. So that's all of the main result. And so if you have any question, maybe I can hear, but maybe just I can continue to the last section. Okay. Okay, so maybe okay. Okay, so in this final section, I would like to mention several possible applications of our Li-Yau type inequality. Okay, so the first example is an elastic knot. But in order to explain this result, first we need to state this an almost immediate corollary, which is embeddedness criterion as in the classical two-dimensional Li-Yau inequality. So in fact, for a closed curve in Euclidean space, we have the following statement. If the normalized bending energy is strictly less than 4 pi star, then this curve gamma must be embedded. And actually, as in the two-dimensional case, this is a direct consequence of the contrapositive of our Li-Yau inequality. Okay. And by using this embeddedness criterion, we can obtain some embeddedness preserving property in elastic flow. So what is the elastic flow? An elastic flow is recently studied by many authors, and one of them is the following form. For a given constant lambda, positive constant lambda, the elastic flow is one parameter family of closed curves satisfying this PDE, time-dependent PDE. So actually, this PDE is of fourth order. But anyway, at least in this talk, this concrete shape and concrete form is not so important, but rather an important point is that this PDE can be obtained as an L2 gradient flow of the energy E lambda defined by the linear sum of the bending energy and the length. And here we have a coefficient lambda. And this lambda directly corresponds to this lambda. But anyway, this PDE can be obtained as a gradient flow of this energy. And of course, due to its gradient flow structure, we have the monotonicity of the energy. So more precisely, any elastic flow decreases this energy along the flow. Okay. So this is one important property. And also, the other important property is that this PDE is fourth order flow, because here we have a curvature which already contains second order derivative, and also we differentiated this curvature twice. So we have here fourth order derivative of the curve. So this is a fourth order, some kind of parabolic equation actually. And due to this higher orderness, we have embeddedness breaking property. So more precisely, even embeddedness of the elastic flow may break in the middle. And this is quite different from the lower order flow, second order flow. For example, the well-known curve shortening flow always preserves the embeddedness of the initial flow, initial curve along the flow. And this is due to the maximum principle. And this embeddedness breaking property is also due to the lack of the maximum principle. Okay. But now by using our quantitative criterion, we can obtain an optimal threshold for all time embeddedness of elastic flow. So more precisely, if we assume that the initial curve gamma 0 has this property, which is a kind of energy estimate, then, roughly speaking, if the initial energy has low energy, then the elastic flow starting from this initial curve gamma 0 is always embedded for all time t. Yes. So, okay, but anyway, it is actually known generally, and there exists a global in-time solution. And this global in-time solution is, in addition, embedded if the initial curve satisfies this energy condition. And this condition is, in a sense, optimal. So in the sense that suitable size of the figure-8 elastica actually gives a concrete example of stationary solution to this flow. And this figure-8 elastica satisfies equality in this criterion. So this criterion is actually optimal in a certain sense. So the proof is actually quite easy. And the key fact is that this energy estimate holds in general. And by using this estimate and by using this assumption, if we have this assumption, by using this general estimate, we have this B bar is always strictly, the initial, the B bar of the initial curve is strictly less than 4 pi star. And then by using this, our criterion, embeddedness criterion, as well as the energy monotonicity, we have at each time slice, the curve satisfies this embeddedness criterion, so the curve is embedded. Okay, so this is actually quite a direct consequence of our Li-Yau inequality. And I would mention that the fixed length elastic flow can be also considered, and this fixed length case is actually more direct. And we don't need to use this kind of estimate, so direct consequence. But anyway, this is a quite direct consequence, almost, trivial application to the elastic flow, at least for experts. Okay, and next, the second application is for elastic network. So, and this network stuff is also recently studied by many authors. And now we give some brief definition. And now we focus on the theta networks, so-called. And what is theta networks? The theta network is defined by a triple of curves, H2 curves, gamma 1, gamma 2, and gamma 3 that meet at their endpoints with equal angle, equal 2 pi over 3 angle. So it's a kind of, it makes a quite homogeneous triple junction, planar triple junction. And these are figures. I think this is quite easy to understand. One of the simplest example of theta network. So we have 3 curves here, and they meet equal angle at their endpoints. And all the angles are 2 pi over 3. But we, of course, we have another more other complicated shapes as like this. So general theta networks are given as like this. Okay. And for this network, we consider a minimizing problem of a kind of elastic energy. And here, the corresponding elastic energy is defined by just the linear sum, the sum of the bending energy and L length. But actually, this is equivalent to considering a general multiplicity, because after rescaling, we can reduce a general case into this case. So this is a kind of general energy. And we sum up this energy with respect to the index. Okay. So this is the total energy what we consider here. And in this context, we also have a general existence result of a minimizer of this elastic energy. So this is a main result in this context. So there exists a minimizer of this elastic energy among all theta networks in Rn. So in Euclidean space of general dimension. And in fact, in the planar case, if n is equal to 2, this result has been recently proved by Dallacqua, Novaga, and Pruda. But they mentioned that in the general codimension case is left open. And actually their method uses the two-dimensionality. So we have actually resolved this open problem here. And the main ingredient is actually our Li-Yau type inequality holds in general codimension. And yes, and that is the main ingredient. But maybe one wonders how our Li-Yau type inequality can be applied to this problem. So let me give you the brief strategy. And actually, this strategy is due to the Lacan-Novaga and Pruden. So the strategy is the following. Now we consider, since we are considering a minimizing problem, we take a minimizing sequence among theta networks. Then, by the boundedness, we have some dichotomy result. What is a dichotomy? Any minimizing sequence is up to taking subsequence converging to one of these two cases. And one is some theta network originally, but the other is, I mean, in a sense, degenerate case. It can degenerate, it may degenerate. And the degenerate case means that one of the component chord shrinks to a point, and this is no longer a theta network. But it's some kind of composite of two drops. Okay. And what we want to show is actually this case has larger energy than this theta network case. And in order to show this case, our Li-Yau inequality plays an important role, because in this case, this curve can be regarded as a closed curve with a multiplicity 2 point. So we have a general lower bound in this degenerate case. And so the remaining task is only to construct some good example which has less energy than the lower bound of the degenerate case. And actually this can be done by some construction. By using the deformation of wave-like elasticity, but anyway, this is a bit technical, so I don't enter the details more. Okay, so in this way, we can apply our Li-Yau inequality to this network problem. Okay, so finally, in the last 5 minutes, I want to explain the possible application to elastic node. And in this case, we have no quite direct application, no exact application, but I think this is still some kind of conjecture. But I think, I hope you found something interesting here. So anyway, in order to mention the study of elastic nodes, I should mention the classical result of Langer and Singer. And this result states that any closed elastic in three-dimensional space is one of the following three cases, or its multiple covering. And one is a planar circle, and one is a figure-eight elastic, planar figure-eight elastica, which I already mentioned several times. And the final case is a new candidates, which are embedded torus nodes. And these are actually very special shape. And there are infinitely many geometrically distinct candidates. But actually, they also showed that among these candidates, the only stable one is the one-fold circle. So actually, in this model, the only one-fold circle can be attained as a stable solution, which it is, in a sense, physically attainable solution. So this model is not sufficient to model these kind of complicated elastic nodes. So how can we model these elastic nodes? In order to model this one, one classical idea is to minimize the bending energy B with suitable constraints on self-Witters sections. And this idea actually goes back to a classical paper of von der Moser. Okay. And nowadays, the elastic nodes are very, I mean, there has a groundbreaking study. So I should mention this result. So first of all, what is a known result about the elastic nodes? Actually, there are quite a few results are known. So first result is the trivial one. The minimal elastic unknown is just a one-fold circle. And this is actually quite not difficult result. And then next non-trivial result is just recently obtained by Gerlach-Reiter-Fonder model, which states that the minimal elastic trefoil is the twofold circle as like this. And actually their result extends to general 2B torus knots. So this is quite groundbreaking study about elastic knot, I think. But actually there are not, I think there are no other results that determine the exact shape of elastic knots in other classes. So, but there are some conjectures. One is the circular elastic knot conjecture, which is stated by Garotti and Olivier Pierre-Louis, who are, I think, physicists, and later formulated by Gerlach-Reiter-Fonder model in a mathematical way, rigorous mathematical way. But anyway, this is quite famous, but quite difficult open problem due to non-trivial extension of the Ferri-Milner inequality. But anyway, and recently we have obtained another conjecture, which we call, teardrop heart elastic knot conjecture. And this is our experiment, elementary experiment, but so this is a composition of teardrop and heart shape. And I think this is the minimal elastic knot in the class of figure-8 knot class. Okay, and these are, however, just about conjectures on minimal elastic knots. But there are other non-minimal but stable elastic knots. And what I want to pose here is a new conjecture on stable elastic knots, which expects that the second smallest stable elastic unknot is the elastic propeller, which we have obtained in the previous slides. Okay, and finally, I would like to show you why I expect this. And this is my, not so sophisticated experiment, but this is an experiment by a springy wire. So circle is a minimal shape. So actually the basic shape is a circle, but now you can make a figure-8 elastic shape. And this is actually stable in plane, but actually this is not stable in space. So if I release this shape, then it turn back to the circular shape. But if we want to, if I try to make a propeller-like shape, then as like this, I can actually make a propeller-like shape, and which is stable. So just by small perturbations, the shape cannot be broken. Yes, okay. So this is why I expect the elastic propeller shape is stable. Okay, so this is a summary slide. So the last slide, and I think the time is almost over, so I should stop here. So this is a summary, and actually we have many open problems concerning this study. Okay, so thank you very much for your very kind attention.
Thank you very much for your wonderful talk and very inspiring talk. Does the audience have some questions? If so, oh, here's a question. Sorry. Oh, if you have a question, please raise your hand or unmute, or maybe I chat. Let's see. Let me check. Oh, there's one. Oh, this is a comment. Are there any questions?
Thanks. Thanks for comments.
Yeah. Okay, I have one question. Oh, you have a question. Professor Kurta-book, please. Julia Kurta-book, please. Is it possible to unmute? Ben?
Yeah,
Ben?
yeah, it's possible. Yeah. Yeah, I
Please
think.
unmute.
Yeah.
Yeah.
Yes.
Please unmute. Yeah.
Can you hear me?
Yes.
Yeah, sure. Thank
Okay.
you.
Thank you for that really nice talk. Your demonstration at the end reminded me of these, I don't know if you have in Japan, these beach tents where there's sort of like a stiff wire that bounds the tent and you have to fold them up by twisting them really into two loops. And it's extremely unstable unless you actually get the twist right. And I don't know whether this is dependent on the fabric kind of holding it all together or whether this is just a property of the wire. But it seems like it might be a candidate for another stable configuration here.
Thank you for your comments. Yeah.
Yes, thanks. Thanks for the comments.
By the way, it's very related to in your last part, application 3.
Yes.
What part do you use? Do you plan to use Li-Yau inequality? Your type of inequality.
Yeah, actually, I don't think we can directly apply our inequality. So this is a kind of, I mean, this is not a direct application, but what I produced in the Li-Yau inequality plays an important role in the study of elastic nodes. So I don't have a direct idea to directly use our Li-Yau inequality, but our result actually partially supports this conjecture because now we have already shown that for any perturbation that keeps triple point, the energy is minimal.
I see.
So it's a kind of a partial stability result, I think. But we have more stability for unknowns. But for those perturbations, I don't think our result can be directly used.
Professor Julia Kurta book. Do you have further questions? You raise your hand.
No, that was my question.
Okay, good. Are there any questions, any comments on this talk? Okay. So Professor Benjamin, how do we say? Just close and go to coffee break?
Yes, we can close the meeting now, and
Okay.
everyone is invited to coffee break. I believe everyone received an invitation.
Okay. So if there's no further question, we will close this session. Thank you very much. And coffee time will start from 4 your time, and 3 in our time.
Okay.
So yeah.
See you.
Okay. Thank you.
Thanks. I'm closing the session.
Okay. Thank you very much for joining.
Thanks.
Thank you for your speaker. Thank you for speaking again.
Thank you.